In the previous episode, we crossed an important threshold. We moved from static geometry to dynamic geometry. Metric structure emerged from coherence gradients. Curvature emerged from non-uniform coherence distribution. And geometry evolved as coherence redistributed. Now, we ask the next necessary question. Are there constraints that uniquely determine how coherence must evolve? If coherence redistribution were arbitrary, stabilization would collapse. If redistribution violated structural balance, threshold would be destroyed, so coherence evolution must satisfy strict conditions. We now identify them clearly. There are 4 structural constraints that cannot be avoided. The first is conservation under closure. If a region is structurally closed, coherence cannot arbitrarily appear or vanish within it. Redistribution may occur internally, but total coherence must remain balanced relative to structural boundaries. Otherwise, threshold integrity fails. The second constraint is locality of influence. Coherence cannot change everywhere at once. Refinement order enforces propagation. If one region redistributes coherence, neighboring regions respond first. Structural adjustment spreads. This prohibits instantaneous global restructuring. The third constraint is continuity. In the absence of rupture, coherence must evolve smoothly. Discontinuous jumps would violate refinement ordering. Therefore, coherence evolution must be governed by differential adjustment rather than arbitrary reassignment. The fourth constraint is reciprocity between geometry and coherence. Curvature reflects coherence gradients, but curvature also influences coherence flow. Regions of curvature affect how redistribution propagates. Geometry and coherence must therefore be mutually coupled. Now, observe what these constraints imply. If coherence must conserve under closure, propagate locally, evolve continuously, and couple to curvature, then its governing rule cannot be arbitrary. It must be a second-order evolution rule. Why second order? Because curvature already reflects variation of variation. Curvature measures change in metric variation. Metric variation measures change in coherence. So coherence evolution must relate to curvature in a way that respects this hierarchy. Now consider equilibrium. In equilibrium, coherence distribution stabilizes, gradients vanish, curvature vanishes, geometry becomes flat. So the governing rule must admit flat geometry as a solution. Flat geometry corresponds to uniform coherence. Uniform coherence corresponds to absence of redistribution pressure. Therefore, uniform coherence must be a stable, fixed point. Now, consider perturbations. If coherence slightly deviates from uniformity, redistribution must respond. Small gradients must produce small curvature. Small curvature must induce small feedback. The governing rule must therefore be linear in small deviations. Non-linearity may appear at large scales, but small perturbations must evolve predictably. Now, consider symmetry. The evolution rule must not depend on arbitrary coordinate choice. Since geometry is emergent, the governing structure must be invariant under relabeling of stabilized elements. It must depend only on structural relationships, not external coordinates. This imposes covariance-like behavior. Evolution must be expressed entirely in terms of coherence, distribution, and the geometry it induces. Now, combine the constraints: conservation under closure, local propagation, continuity, reciprocity, coordinate independence. There are not many structures that satisfy all of these simultaneously. In fact, once curvature is the geometric encoding of coherence gradients and coherence redistribution responds to curvature, the evolution rule becomes heavily constrained. The simplest rule that satisfies these conditions relates curvature directly to coherence density. Curvature variation must track coherence imbalance, not arbitrarily, proportionally, but also respecting conservation, which means curvature divergence must balance coherence redistribution. This is the structural heart of gravitational-like behavior. We are not inserting known equations. We are identifying the minimal relational form required. Curvature must respond to coherence density. Coherence redistribution must respond to curvature configuration. The coupling must preserve conservation. Now consider dimensionality. Earlier, dimension emerged from minimal generating basis. That dimension constrains the form of curvature. Higher dimensions allow more independent curvature modes. Lower dimensions restrict them. The governing rule must be compatible with the dimensional structure derived earlier. So coherence evolution is dimension sensitive. Now consider scale. At small scales, coherence fluctuations may dominate. At large scales, averaged coherence distribution governs curvature. The governing rule must reduce to smooth behavior under coarse graining. Otherwise, macroscopic geometry would be unstable. This introduces a consistency requirement across scale. Micro-level coherence dynamics must average to macro-level geometric evolution. Now consider what happens if coherence concentration becomes extreme. Gradients steepen, curvature intensifies. If redistribution cannot compensate quickly enough, stabilization threshold may locally fail. This introduces the possibility of structural singularities. But even singularities must respect conservation and propagation. So breakdown cannot be arbitrary. It must follow structural constraints. Now pause. We have not written any field equations, but we have imposed constraints that dramatically restrict what such equations could be. Any viable geometric evolution rule must preserve closure balance, propagate locally, evolve continuously, couple curvature to coherence density, remain coordinate independent, respect dimensional structure, stabilize uniform coherence. That is not an empty list. That is a narrow corridor, and inside that corridor only a small family of evolution rules can exist. This is the turning point of the series. Until now, we derived geometry from structure. Now we constrain its evolution. If the resulting evolution law resembles known gravitational dynamics, that resemblance would not be coincidence. It would be structural inevitability. But we must remain disciplined. We are not declaring equivalence yet. We are establishing constraint compatibility. Now step back. From difference to refinement, from refinement to stabilization, from stabilization to metric, from metric to curvature, from curvature to dynamic evolution, from evolution to structural constraints. We have climbed without assumption. Each step followed from the previous one. Now, the next question is unavoidable. If only a narrow family of geometric evolution rules satisfy these constraints, does one of them match the structure of general relativity? And if so, does that mean gravity is not fundamental, or that gravity is the geometric projection of coherence dynamics? That question belongs to the next episode. But now the stage is set. Geometry is emergent. Curvature is emergent. Dynamics is constrained. We are no longer describing abstraction. We are approaching the threshold where structural inevitability meets known physics. And if the match holds, the interpretation of space-time changes completely.